Okay, so Unit 1, we should start with Chapter 2 in the book. This is one-dimensional kinematics. So kinematics is explaining sort of how objects are moving, how fast they're going, how much distance they traveled, how much time it took, but not necessarily why. That will be when we study forces, that'd be called dynamics. So we're studying kinematics. So our rules for right now, for Chapter 2, we're considering motion in a line. So it's merely back and forth motion. Okay. And we're considering objects that act as a point. Which will be the first of many times I tell you that this doesn't exactly mimic real life, but this is what we're going to assume for this class. For the most part, we also ignore air, and sometimes we ignore friction. But we know those, of course, occur in real life. But when I say we're considering objects that act as a point, so like talking about a car moving down the street, you know, just the whole object as one thing. Don't consider the extra wheels moving separately. That's something we'll talk about in another unit, but just a point object moving. Okay, so some basic terms. Reference point, got that. Just a point where measurements are made from, often used as the origin on our coordinate system. You know, if I say the car is 10 meters east of the tree, what's the reference point? The tree. Okay, we've got a few terms here that deal actually more with Chapter 3, with scalar vector, and just sort of writing out that notation, any variable letter, but we put this little vector hat on there. Mention that. Okay, so scalar, maybe you remember this from physical science. It just has a magnitude, it's just some amount. Temperature 23 degrees Celsius. Okay, it's just 23 degrees Celsius. Or a distance, something is 5 miles away. It's just an amount away. It's 5 miles. So that's a scalar. As soon as you put a direction associated with it, now it's a vector. And there are some semantics difference here, like distance and displacement. You might think are the same thing, but technically no. Displacement or position is always going to have a direction associated with it. So 6 meters northeast. Okay, got a direction, now it's a vector. Maybe, do you guys remember in 9th grade when we did like the ruler things we made you do? And we added vectors head and tail? Okay. So we'll get more into that in the next chapter, but for this chapter, we will still talk about vectors, but there's going to be a straight line back and forth. So for the most part, we can explain our direction as either just a positive or negative sign. And again, you see the little vector hat as something that means a vector. Okay? So I just mentioned position and displacement. These are vectors. They have a direction. And here is one of our first formulas. Displacement. This is a basic one. Do you remember what Greek letter this is? Delta, do you remember what it means?
Change.
Exactly. Okay, so whatever I stick after this, could be temperature, could be time. This is changing position. So it just means final minus initial. So, or in this case we use 2 and 1. So that's it. And we use the vector hats on all of them, but displacement was the final position minus the initial position. So I can say I'm 10 feet away from the door. Now I'm 12 feet away from the door. What was my displacement? 2 feet. And this way. So those were both in the same direction, so we can kind of use positive values there, but what if they're not? For example, this one. Car's initial position is 6 meters west of a tree, and now it's 10 meters east of the tree. What's the car's displacement?
4 meters east.
meters east?
16.
16 meters east?
4 meters east.
Well, which one's the final? The 6 meters west or the 10 meters east?
10 meters east.
So the 10 meters east is our final, and usually, we would make east positive. It's really irrelevant what you make positive and negative, so long as you're consistent, but we're pretty much always going to stick with things that are east or right or up being positive. So 10 meters east was our final, so 10 minus 6 west was initials, 10 minus minus 6, 16. So be careful with your directions. And since this is a vector, it would be nice that we put on our direction 16 meters east. All right, time interval. Almost always we're going to have our initial time just being 0. So pretty much the time is the time interval. Again, either final minus initial or second time minus first time. Sometimes you'll see this. This is a 0, little subscript 0. You know how to say that? You ever say something like this in chemistry? Like, you don't say T0, you say T naught, just meaning the time at 0. So our initial time, when it was 0, T naught. Anyway. All right, so we also sometimes go through checkpoints of the book. So if you got a book, get it out. Okay, so here are 3 pairs of initial and final positions, respectively along an x-axis. Which pairs give a negative displacement? Which is essentially this question all over again. All you got to remember for displacement, final minus initial. So can you find one that's going to be negative? They said here are 3 pairs of initial and final positions, respectively. So the initial one's first.
B and C.
So in fact, that's the only one that's not. So yeah, B and C. I mean, B would be -7 minus -3. And then C would be -3 minus 7. So both are going to give you negative values. That's it. So hopefully I've got in your head displacement, final minus initial. Okay, a couple other terms. Oh geez. Where are we going? Okay. Speed and velocity. And little line above the variable doesn't mean average. This really should also have a little vector hat. Well, this one should have a little vector hat. But that's your main difference. Average velocity is a vector, so there will be a direction associated with velocity. Average speed is a scalar. Okay, so you just need to know your total distance.
Is the S on the average speed supposed to have a line above it, like the V?
No, well, yeah, it is. That's for average.
Oh, above it, because it's
Yeah, that should too.
negative.
And this one should have a hat. And hopefully you also remember from 9th grade doing some of those motion graphs, and whenever we had a position versus time graph, we very often asked you to find the slope. Well, what did that mean? Well, that was the velocity. So we'll see a few differences in these two in a moment. In our units, some of your summer work dealt with using appropriate units. Metric units here, standard metric units would be meters per second. Okay, so here's our example problem number 1. I can't fathom you'll be able to fit it on this slide, so you might want a separate sheet of paper for this. and I'm gonna need you guys' help telling me what the numbers are. Trying to catch up in technology. Okay, so let me just read it before we get started. All right, so a motorist drives north for 35 minutes at 85 kilometers per hour and then stops for 15 minutes. He then continues north, traveling 130 kilometers in 2 hours. So really, how many like segments of this trip are there? Drives north, 35 minutes at 85 kilometers per hour. Okay, I would consider that like part one of the trip. Then he stops. Little part, but I still consider that separately. And then he continues again, traveling 130 kilometers in 2 hours, which would not be the same speed. So we've got like 3 parts of this trip, and we're going to try to help keep them separate to analyze this problem. So what is his total displacement? First question. What was our formula for displacement?
This is
That's our velocity.
final.
That'll be our next one. So for displacement, we're doing final minus initial. Do we even really know where he started? Not really. So in a case like this, you're just going to assume he started out, point 0, wherever that may be. So we already assume his initial spot's 0, so we're just going to figure out where he ends up finally, and that will be the answer. Then we want to know his average velocity, and we want to graph it. Okay, so our first goal is total displacement. Let's see if I can keep this organized. Okay, so we got part 1. Okay, you guys have the notes. Part 1, what was relevant information for part 1?
85 kilometers per hour for 35 minutes.
Okay, so our speed, velocity, since it's going to be a straight line anyway, 85 kilometers per hour. And what was the time?
35 minutes.
All right, part 2, relevant information.
15 minutes.
Just stop, 15 minutes. And part 3.
Distance 130 kilometers. In 2 hours.
Okay, so this is all our relevant information. Part 1, we want to find our total displacement, which we almost know all the displacements for each part. I mean, we got 130 kilometers, and we got nothing. But our first goal, I guess, would be to tackle what's the displacement for this part 1. Now, before we get started there, what do we notice about the units?
You need to change the hours to 120.
Yeah, the times don't match. So we got to pick a time unit we want to go with, either minutes or hours. And it really doesn't matter. We have 2 things in hours and 2 things in minutes. So let's just go with hours, because we can do that one in our head pretty easily. I should close that. 15 minutes. How much of an hour? Quarter of an hour. And 35 minutes?
0.5833.
You got it? 0.58?
Yes, sir.
Thank you. I always do require calculator help. And if you modeled through the summer work, a lot of that was unit conversion, dimensional analysis stuff. So hopefully you're with me on converting units. We got 60 minutes in an hour, so we're just dividing by 60. Okay, so our last step then, is to find the distance traveled for part one. So there's our formula for velocity. We've got all this info. We've got our 85 kilometers per hour. Our distance traveled is what we want to figure out, and our time was 0.58 hours. If I haven't said this yet, I'll say it again. This is a math class, just FYI, with some fun science sprinkled in. So, math's not your favorite. You're going to be in for a lot of math. If math is your favorite, which I hope it is, and science, then you're in the right spot. All right, so we're solving for D. So we're going to multiply 0.58 to the other side, and our distance traveled for this section is,
39.
what is it?
39.6
Thank you. Unit?
kilometers an hour.
Kilometers.
Just kilometers, this was our distance.
Yeah.
Okay, so all this work, and we can finally get an answer to part A. What was the total displacement? Well, it was in a straight line. We know the initial spot was 0, so we're just going to add up all the distances traveled, which is this
179.
plus 0 plus 130, which would be,
179.
well, I'll write it out. 130 plus 0, going backwards, plus 49.6. Thank you, 179.6 kilometers. Ta-da. Okay, that's part A. Questions, comments, concerns? A little bit tedious, but hopefully that's pretty straightforward. Just, good record keeping mainly. What was question B?
How's the average velocity?
The average velocity? Okay, average velocity. Well, we've already sort of used that formula. That will be our displacement over time, which same thing as distance. So we already know our displacement, just found out in part A, 179.6.
It's raining.
Oh, it's like some thunder. What's the time we're going to throw in here?
2.83.
How'd you get it?
I know.
Just, yeah, add them all up. We need the total time. That's the total displacement. We need the total time traveled, including part 2. So 0.58 plus 0.25 plus 2 is, what'd you say, 2.83. That would be a fun time to say that. Probably unlike chemistry for you guys last year, don't really kind of offer sig figs. They are aware of it on the AP exam, so if your numbers don't have any decimal places to begin with, don't leave 17 decimal places in your answer. As long as you simply avoid that, then you should be fine. What do we have for this answer?
63.46.
And that would be in what unit?
That would be in kilometers per hour.
Kilometers per hour, okay. Ta-da. Still one more part. What's our last part?
Graph.
Graph, all right.
Position versus time.
Okay, I need you guys to remember all that info. You got it on your papers. I'll get that little line out of there. All right, position versus time graph. All right, so if you're doing a graph, typical graph things, put your labels on there, put some units for each axis, and come up with an appropriate scale. So, exactly, you just told us the total time was 2.83. All right, so let's maybe just go to 3 hours. We'll mark off every, all right, every half an hour. 0.5, 1. Okay. And what was our total distance?
That was like 79.6.
179.
So we're hitting.
I'm gonna go even bigger. We'll go to 250s up to 200. Doesn't matter. Okay, so just, look back at your information. So part 1, I've already forgotten how much time was part 1? That was 0.58. Okay, and then how far did we go in that part? 85 kilometers. So what would my graph look like if I'm moving?
49.6.
Okay. I'm moving. And that first part was what, 0.58? There you go. You are moving forward, so you are increasing your position. Don't make it a flat line. You didn't just stay at 49.6 kilometers. All right, and then part 2 is how much time? 15 minutes, or 0.25. Okay, so part 2, we need to add in an extra 0.25. Do it 0.83. So, somewhere over here. And we were still. Does that graph look like? Flat line. And you already told me that the end point's 179 kilometers at 2.83. Total amount of time, just connect it all. Sort of. Okay, 14, page 14, checkpoint number 2. It says in sample problems 2-1 and 2-2, which we're not going to read those, but all you need to know is that this truck started at position X1. So it says, suppose that after refueling the truck, you drive back to X1. So you went somewhere, you got some gas, you drove back. So you're at the same place where you started. If you drive back at 52 miles per hour, what is your average velocity for the entire trip? Do you feel like there's missing information there?
Yes.
Yeah.
Like what?
Like maybe the time it took to get to X1.
Yeah, like
the distance.
maybe the distance to X1, the time to get to the gas station,
Just
how fast were you going in the first place?
Like the displacement is 0.
But you actually don't. Now, if it wanted to know the average speed, you would need to know the information like that. But semantics comes into play here. You gotta be careful with the wording. This says velocity. So the definition of velocity is displacement over time. What is a displacement?
When you leave from one point and go to another.
Yeah, if you leave one spot and go right back to it, your displacement was 0. Your final position, I could be 10 feet away from the door. I walk over here, walk back, I'm back to 10 feet away from the door. My displacement was nothing. Doesn't mean I didn't move. I did move. but my displacement, so technically, my average velocity is nothing. Be careful for if they say something about average speed. You could calculate your average speed, but velocity is a vector. And basically I went in the positive direction for half the trip and the negative direction for the other half of the trip, so that cancels out. So my average velocity is nothing. That's a common physics question we like to throw at you. If you end up back where you started, your average velocity was nothing. Now I want to mention something else you'll see in the homework. Maybe. Tertiary. Okay, let's say it's halfway. Okay, here's you in your car. Absolutely not texting, going this way. And for the first part of your trip, you're going, let's just say, 50 miles an hour. And then the speed limit changes to 30, so now you're going 30. This is like one of your homework questions too. So for half of the distance you go 50, the other half of the distance you go 30 miles per hour. What is your average velocity? Your instinct is going to be to say 40. Well, that's right, smack in the middle. Just add it up. 50 plus 30 divided by 2, 40. Why can't you do that?
Because you're going 30 miles an hour for longer than you know.
Exactly. It's almost like a, like a weighted test average. You got to count part of it more. And time is what we need to consider. Well, I didn't go 50 miles per hour for an equal amount of time as I went 30 miles per hour. If I'm going 30 here, I'm going slower. It's going to take me longer to go this far than it did here when I was going 50. So be careful. You would have to calculate the total distance, the total time, to do your displacement over time to get your average velocity. So just be careful that you don't fall into that trap too. Now, if it said you went 50 miles an hour for half the time and 30 miles an hour for half the time, then you can just average them like that. But be careful in your homework for a problem like that.